All right, welcome. As you know, my name is Craig Sipes and I'm the STEAM coordinator for Local District East. And joining me today are, I'll let them introduce themselves.
Hi, I'm Kirsty Hernandez. I am the STEAM coach for the Northern community of schools. So Boyle Heights, Lincoln Heights, El Sereno, and East LA. I always forget one.
Hi, I'm Lillian, and I'm the science coach for the Huntington Park, Walnut Park, and Vernon community of schools.
Thank you, Kirsty and Lillian. And so today we are on number 4 of the 4-part series. We are pressing for evidence-based explanations. And when I say we, that's because these are teacher moves. We're talking about the ambitious science teaching practices. So to start off with, let's look at the Squirrel Scale. How are you feeling today? Where are you on the Squirrel Scale? So we're going to give you a second. We're going to do a chat avalanche. So go ahead and get ready to press enter on a number. Select a number, type it in, and get ready to press enter of what you're feeling today. All right, I've got my number. How about you? Ready? 3, 2, 1, enter. All right. Oh, Kirsty, you're to 9 now. That's good. You were to 8 yesterday. I'm tracking your progress. Good. Oh no, you weren't with us yesterday. No, you were probably
me.
at a 9. That was you.
It was me.
Okay.
Yeah, I was at 8 yesterday.
You were 8. Oh, now you're a 6. Oh, sorry about that.
I don't know what a 6 is, but it looks cute.
I'm a 6.
And Ruben's a 6 too. All right. Christina's a 5. Is that a good thing or a bad thing? Are you relaxing or are you feeling pooped?
No, it's been a taxing week. We had grades due this morning, and so there was a lot of grading involved.
How about you, Evelyn? Same?
Oh yeah, same thing. Grading.
Yes. Oh, I love grading. All right. Well, glad to see that you're here today. So today, the objectives, as we consider how to press for evidence-based explanations, we're going to talk about gotta have it checklists and how you might use them and how you might support students in using evidence to account for different aspects of students' explanatory models and how to engage all students in authentic disciplinary discourse around constructing and defending explanations. So you know the norms. We'll continue on. And the instructional levers are the same. We're continuing to look at clarity of learning goals. We're digging into precision of pedagogy and we're continuing to think about how we can elevate student voice. So standards-based instruction always starts with the DCIs, with what students will know, but this is starting from the standpoint of what are students trying to figure out? So how can we set up learning so that students are figuring things out? And they do that by engaging in the science and the engineering practices, the SCPs. And the question there is, how are students figuring it out? And then how are students thinking about it? That's the CCCs, engaging in the cross-cutting concepts. And all of this is in service, all 3 dimensions, all of the standards are in service of students constructing explanations and models of anchoring phenomena, of events, anchoring events, students figuring out phenomena. So once again, the local district foci, we have 2 different categories, student moves and teacher moves. The student moves are the practices. And so here we're looking at 2, 6, and 7. Today we're gonna dive into those a bit. And so we're really looking at how do we support that. And this is all building up to that. So we started our journey. This is PD number 4. We started our journey with planning for engagement around important science ideas. That's ambitious science teaching practice number 1. We moved into then, how do we elicit student ideas? Then we moved in, how do we support ongoing changes in students' thinking? And now that we've done those 3 things, then we're moving into the point here. We want them to come up with supported answers. So how do we press for evidence-based explanations? And so that's where we're at today.
All right, so we're looking at ambitious science teaching practice 4, pressing for evidence-based explanations. And as you can see in this diagram in the center, pressing for evidence-based explanations, we have ambitious science teaching practice 2, as we focused on eliciting student ideas and modeling. So we understood that the use of modeling helped us see students thinking and gives us a vessel to see how student thinking may change over time. So this is important because explanations, which are our focus for today, we can see how closely tied they are to modeling, and also allows us another way to see the change in student thinking over time. So there's 3 sub-practices in pressing for evidence-based explanations. The first is called co-constructing a gotta have checklist, which Craig mentioned earlier. The second sub-practice is called pressing for evidence-based explanations and models. And then finally, assessing for understanding. So here's an example of a student initial model to the lawn chair flight phenomenon. Inspired by the movie Up, Eric Rohner took it upon himself to make it a reality. Using helium-filled balloons attached to a lawn chair, he successfully took flight and managed his aircraft to end with a safe landing. So students were asked to draw a model and explain how Eric was able to do this. So after a series of lessons, students and the teacher co-created a gotta have checklist for their final models and their explanations. So this checklist is going to help students understand what is expected to be included in their final explanations and models. So using this checklist, students produce a final model. And again, it's a nice little checklist that's thorough, that addresses, if you notice, certain ideas and concepts. And it's not just a list of vocabulary words. So for our first breakout activity, you're going to be looking at an example of a final model for the lifted chair phenomenon. And you're going to go into breakout rooms to discuss the 2 questions listed on the side. How does the gotta have checklist help students refine their initial models? And how is a gotta have checklist different from a rubric? So are we going to go into breakout rooms? How many participants do we have now? Should we go in a breakout room?
We have 5.
Okay, I think maybe we can just do it all whole group.
That works.
All right, so just take a look at, take a moment to look at this sample final explanation and come up with answers to the 2 questions, and we'll kind of share out and give you about a minute or 2.
The participant slide deck is also in the chat. So if you want to open that up, you can kind of flip back and forth between the final model and the gotta have checklist.
Thank you, Kirsty.
What grade level would this be, Lily? You're on mute.
This one, I think this is this an 8th grade unit?
It's middle school. States of matter are really covered in 7th grade.
Oh, it's a states a matter? Okay, so then, yeah, it would be.
If you're, well, it depends. Yeah, we'd have to really look.
Mhm.
You're talking about
Forces. Oh,
this
no, they're
forces
forces.
one.
Sorry.
Forces is eighth grade,
Yeah,
right?
8th grade.
Yeah.
You're right.
This is ninth grade, right? Because
It's
it's
physics.
including, yeah, because it's including this is ninth grade physics.
I know there are some forces for eighth grade as well.
Yep.
I think that it must be 8th grade. 7th grade, we don't cover forces.
Yeah.
Yeah, this is ninth grade.
Oh, should ninth grade is physics? We have ninth grade physics? I'm sorry.
Yes,
Yes.
Oh,
you can have physics in ninth grade. This happens to be a ninth grade physics class.
Mm.
Okay, so what do we notice about the gotta have checklist, and how might this support students in refining their models? Christina, did you raise your hand?
Yes, you know what? I really like this. I like it because it says I. So it's like they're taking ownership that I have
Mhm.
included these items on the checklist. And I really like the way those I statements are stated, to not be redundant, but I really like that. Whereas
Yeah.
I think a rubric would be more of, there's a grading criteria, or there's some kind of criteria based, based on, like what's the teacher expectation and how they're going to be graded. But this is just a quick checklist. Does my model have this, 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 and this? And it kind of like keeps them oriented to what their goal and objective is for the model.
Yes, thank you. That's a great analysis and noticing, Christina. Thank you. And so one of the things that we mentioned also with rubrics, what other things are included in rubrics beside that are different from a gotta have checklist?
I just myself, I'd see a rubric as, it's the grading criteria, what Ms. Fox was saying. It's the
Mhm.
quality of the work. The checklist is a great thing, as Ms. Fox, I could say what she says, but it focuses them on what they need on it. It directs them what they need on it. They cover it. And if they do cover all that, then you go see the quality and with the rubric to what quality is it. And then they'll get the letter, I guess a grade, B grade, or C grade. But if they cover all those checklists, it's going to be probably, somewhere between a C or a B for sure. And if they put quality on it and do the X or whatever the rubric says, that just guides them more. And then that's about it. That's all I got to say.
No, that's great. Thank you. Thank you, Ruben. And so, other items that might be included in a rubric could be, like grammar and syntax and things that are not the content part of it. So there are some, and then of course that grading scale, as you mentioned, and, the different levels for each. So yeah, and then, and one of the conversations that we've had yesterday with elementary was, that sometimes, a student can include force or mention force in their explanation, but is the force correct? Is it identified correctly? Or is there a relationship being demonstrated? And so with the checklist, it does help them to stay focused and really pull out and explain those important points and key ideas. Great, thank you. So here are a couple more tips for the gotta have checklist. So it should be co-constructed by the students more than the teacher. So, create a poster, have a poster has to say, okay, so what should we include in our explanations? We've gone through this whole section here, or these lessons. What are the most important things we should be including in this explanation? And so have students generate that with your guidance. And again, this list should grow over the course of the unit. And it should be composed of ideas or relationships that students now believe are important to be in the explanation. Including the word how sometimes helps you as a teacher to express the items as ideas rather than words. And when students are creating their final explanatory models, make sure they have access to the checklist. So, it's not, you're not giving them the answer. The students still have to put it together and put those ideas together And, with their own learning, it'll all make sense. It's not like you're telling them exactly what to say and how to say it. They still need to make sense of it all.
Oops, hello.
What happened?
I don't know. I'm gonna
Really?
pause.
Hi, Ms. Martinez.
Hi, how are you?
All right. So
Fine.
what we're going to do now is go into another breakout room activity. I think we have a little bit more people for it. And we're going to try and develop one of these gotta have checklists. So what you guys will see is in the participant deck, there is a grid for grade 6, 7, 8, and then biochem and physics of different anchoring questions that were included as a part of the curricula. The great thing about secondary is we are all kind of content experts. We know our stuff. But what we want to do is we kind of want to take that frame of mind of the student. As students go through a unit with you, what would be the big ideas that they pull out and that they would think are important to answer some of these guiding questions? All you have to do is pick one. So if as a team, you guys decide, we're going to focus on, 7th grade, the HMH question, then that's how you would create your gotta have checklist. Okay. Are there any questions?
Do you need me to create the breakout rooms?
Yeah.
I am
Okay.
making them right now.
Oh, okay, great.
Yeah, sorry,
I know.
almost done.
Can you explain the instructions one more time? I'm sorry. It's after school,
Yes,
after a
yes.
long nights of grading. One more time, please. What are we doing in the
Yes.
breakout rooms?
So once you go into your breakout room as a team, you guys will agree upon which anchoring question you want to create a gotta have checklist for. So it might start with answering the question, thinking about the big science ideas that you need to answer this question, and then creating that gotta have checklist. I can, like momentum of a car crash, I can show conservation of momentum, something like that. So you're taking those big science ideas and creating that gotta have checklist, similar to what we saw here. Those big science ideas that really help us answer that question or explain that phenomenon.
And you have these slides, they're in the chat. So feel free to open them up. You can open up either the main deck, or are they in the participant copy? I think they are.
They are. They should be in the participant copy as well.
Yeah. All right, does that make sense? Okay, all right, so we're gonna open the rooms. There'll be a 6th grade, 7th grade, 8th grade biochem and physics room, and then you get to choose which room you're gonna go into. If you happen to go into a room and nobody enters after like 30 seconds, then maybe go to another room. All right, we'll see you in 7 minutes. Oops, I almost ended the meeting.
I don't have the option for the break-in rooms. Oh,
How about now?
is there?
Mr. Can I just stay in my room, like work until like for the high school?
Yeah, you wanna just work alone? That's fine.
Yeah, thank you.
I'm going to join Ruben.
Okay.
All right, I believe everyone is back. So would anyone like to share out about that process and thinking about what big ideas need to be present?
Yeah, more about the process rather than the specific list that you generated.
Mhm.
I'm thinking when I processing it, like, wow, it is even harder. Like, we thought it much, like giving the direction to the students is easier, but like thinking, what do I really like to give to my students? My students makes my mind keep on like, okay, now let me change. I don't want that. Like, it takes me more like, okay, yeah, I give the direction, but if I will not give them the specific list, I guess my students will not get it either, because I myself is like, I changed actually a couple of times what I really wanted.
Thank you for sharing. Anyone else in their process?
We were in the 7th grade group, and our question was, we do HMH, chemical processes. So the question was, what happened to the matter and energy that were in these fruits when they were first picked? So I'm assuming that we were wondering if there was like a picture that went with this question. Like, I was wondering, well, are the fruits already in the process of spoiling? Are the fruits, have they been cut up and put into a fruit salad? So we were kind of like wondering, was there like a picture missing in our prompt? Because that would have helped us kind of like guide our gotta have checklist.
Okay, so yeah, having that complete understanding, like just like students, right? If they don't have that picture, like I know my kids all the time, every time we've revisited our phenomenon, they're like, can we just watch it again? Like, yeah, I kind of remember what we were doing, but can we really just watch it again? And it was always like, all right, yes. We haven't looked at it in depth in a while, so we can do that. So having that present would have been helpful for you guys, and in turn would be helpful for students as well. Thank you for sharing. Anyone else? Last final thoughts?
My
All right.
final thoughts is this. I mean, I'm so, like, I'm kind of confused, but I think confusing is always a good thing. That's when you're thinking about it, you're learning about it and all that stuff. In a phenomenon, I can have a phenomenon and, why did the Titanic ship sink? Okay, I guess that would be a phenomenon. Okay, the Titanic hit a ship, but why? I mean, I guess that's a anchoring event or a question or the phenomenon, you come back to it. But if I was doing evolution stuff and I wanted to say, what are the main evidence of evolution? And, as the book, I'm looking at the book again, I outline my course. Sometimes I use a little less in there or extra credit, but, fossil evidence supports, the history of evolution. But if you're talking about fossils, I mean, to come back to the phenomenon, is that worthwhile time in the class? And again, Lily, I'm big on time always, and I'm always, it's really tough to always come back to phenomenon or checklist, because the checklist on the opening thing is very important, but every single other activity, you don't have the time. It's just not reality in it, because you can't get to it every time and self-analyze and do it. But on any type of big event, I think it's a great idea, all that stuff. But being anchoring question that we want to answer at the very end, what are the main evidence that supports the theory of evolution through the process of natural selection? But if I had a phenomenon, well, I guess that's good, but I don't know. I still want to go back to that major theme that I want to. So that's where I'm kind of sorting it all out still before I retire. I'll get it when I retire. Oh, I got it. But anyway, I'm just jibber jabbing, babbling a little bit. Okay, I'll stop.
No, I think you're on the right track, Ruben. You're really trying to consider how do you make it work in the time that you have, and you're considering that you want to make sure that the students understand the whole main point of the unit and the standard, right? That's what you're saying, and that's exactly on point with what this is all about. And that goes back to ASTP, the ambitious science teaching practice number 1, which is planning on engaging students with with big ideas. So the phenomenon, the anchoring event, you said it very well. Anchoring event, if it doesn't cover that big idea, then it's not a good anchoring event. And so we want to make sure that the anchoring events that we select are ones that are going to engage students in those big science ideas in the
I'm
standards.
looking at, excuse me, I just like to say this. I'm looking at that last sentence on the creator gotta have triplets, but it says for the given phenomenon or the anchor question. And I'm definitely going more with the big anchor question instead of the phenomenon. Then phenomenon to me is like a subcategory of the big anchor question. Is that okay to see it that way, or?
So the reason that it said that is because Discovery, like for this one, it didn't really offer an anchor question, but it was more about the phenomenon of the car crash.
Correct.
Typically, whatever your anchor question is tied to some sort of phenomenon. So like wildfires are difficult to extinguish. The phenomenon would be that like wildfires burning in the hills of California. So that's your phenomenon, but your question is what really guides that and ties it down.
But the unit though would be more like something like that, would be, human and interaction condition on the environment, which is like from climate change to, pollution problem, overpopulation, all those things. And those things to me are kind of subunits of that overall unit. So if maybe, I guess that overall unit should have maybe 4 overall anchor questions, or maybe 2 or 3 different phenomenons in there, because if you just have one phenomenon, it's not going to cover that big picture, or there's different aspects of it, so again, that's where my getting confused as in how to make the best using anchor questions, phenomenon, whatever, and then coming at and then teaching it, but then seeing the big unit, what they want to, the big hittings, what they want to do. It's kind of, I don't know, you got to hit it, because if you just do on what makes a car crash or whatever, that's only one aspect of forces. But again, I guess that because of all the forces, but within that unit, there's forces, there's speed, there's velocity, there's all kind of stuff in it,
And all of that would be tied to explaining that car crash, about why the car with 0 velocity or acceleration versus the car with, differing accelerations or velocity have different impacts than, 2 cars speeding at each other. Things like that. Inelastic collisions. Why does it look worse when the cars kind of T-bone and stick together versus, you sideswipe a car and just hit the mirror? So all of those things can be covered. And I think you're saying like the anchoring phenomenon is hard, but having those 2 or 3, those are those investigative phenomenon, those mini units that you were really talking about. So you have this big picture, and then each of these mini units kind of come together to explain this big picture again.
Yeah, and that sounds good. But if you have that, and as that's your big thing about a car crash, you have forces and speed and acceleration, and then you expect the students to know that after the 6 weeks of physics and put all that in there, you're asking a lot for that student, 8th grade student, to do that. Now, can they concentrate on 3 or 4, just the main parts of it? To me, I find that's more realistic. But when you're trying to get every single thing in there to really understand the whole thing, and that's going to take a lot of time. But again, a lot of these people, kids, to have that many different aspects of physics forces to solve that, you're asking for I don't know, that's a lot from the students to get, at the end. But I don't know if it's a piecemeal, but if they were able to get it, they got it, or they're sharp, or I did my job, I guess, Okay. I'll leave it there.
All right. Well, thank you for sharing. I appreciate it. Really ignites this conversation, has us all kind of thinking about how do we use these, right? How do we use these in our classrooms and really go back to what we're doing? So I appreciate your comments, Ruben, and everyone else for sharing out this process and how it kind of went for you. All right, so what we're going to go into now is we're going to look at a few videos of classrooms co-creating this gotta have checklist. So the first 2 videos are the same 5th grade classroom, And in this first video, we're going to see a small group discussion. So the teacher is going to go over what, instead of they call a gotta have, they call it a must have. So what is our must have? What is a must have? And then we get to listen into a conversation in a small group. So let me make sure my sound. Sorry, let me try and share again to make sure my sound, oops. One more time. Share sound, perfect. All right.
People. Model, maybe. No, you draw gravity too. It's important. Oh yeah. Maybe pattern maybe like pattern of like yeah. Our whole unit is Mount Nose. Pattern of Earth and sky. Maybe we should include Mount Nose. Patterns we see. I don't know. Mount Nose. Mount Nose. I'm not gonna write Mount Nose. Yeah.
Okay, well, well, yeah, we're gonna need that, but that's
maybe patterns we see. Okay. I know because when we're doing the rotation. Nose is crucial.
Constellation stars. What do you
okay.
You're gonna draw?
Mount Nose is crucial for everything that we've done in this unit. Model, do we need? Ooh, what about directions? Because like looking south, looking west, looking east. What about model? Yeah, sure. Yeah. Okay, good too.
What is a must-have that you feel you need to have to answer the question, what did you learn about the relationship between Earth and stars that helped us solve the problem of the missing artifact? Soliana.
Constellations.
Constellations. So do you mean that as part of your drawing and your explanation, or both? Both.
Right, so then we're going to go to the second part, which is kind of the teacher summarizing everything that they did in that whole group discussion.
So this is a suggested list of must-haves. Meaning it's just to give you an idea of what you might want to include on your model to be able to explain the relationship between the Earth and stars. Now again, the front is a drawing with some little text boxes or explanation, and the back is where you write your explanations to your drawing. Okay?
So right at the end there, we were able to see kind of the example of the whole class. So after that share out and whole group discussion, and then what the individual groups had come up with for their models explanations. So now the last video we're going to look at is a whole group secondary example of creating this gotta have checklist and really paying attention to how the teacher kind of guides students through this process, because like we said, it wasn't this easy process, right? We had to really think about what did we want. So how can we guide students through this instead of just having them kind of tell us the answer that we want to hear?
There we go. All right, so what could be one thing that's helping to cause those different flame heights? We'll start us out and then we'll go to Liz. And so something involving sound waves. And so instead of just making like a list of words, we're gonna give us just a little bit more substance. And so something involving sound waves. Where do those sound waves come from? Okay. What is the speaker doing? How do we know? Okay, so we could say how vibrations from the speaker create. And so if we wanted to say sound waves, would that be longitudinal or transverse? And so we'll say create longitudinal sound waves. All right. What were you thinking, Luke? So we need the latex on there. So involving the vibrations from the speaker, what could the latex be doing? It could be amplifying the sound, and so maybe as a sub point, we'll put latex interacts with sound waves. Let's see what else.
All right, so that video may have been hard to hear, and I'm sorry, I made sure all the volumes were up. But again, students were kind of giving vocabulary that they had remembered, and the teacher was guiding that, asking them, well, what does that mean? And what is that kind of, what do we mean by that? What concepts can we present with that? It wasn't just about sound waves, but rather, how would we, what does that mean by sound waves? What do you mean? Those vibrations, that latex, what does that latex do? Asking those guiding questions to co-construct this. All right. So we want to remember our goals as we continue to think about pressing for evidence-based explanation. So we're supporting students in using evidence from different areas and different parts to have this explanatory model. It's not just evidence from one investigation that's going to explain everything from the whole unit, but rather lots of different lessons and things and experiences that they've had throughout the unit to construct this elaborate explanatory model. We want to hold students accountable for that too. They're going through this learning. We want to hold them accountable for all their learning and not just one part of it, not just that, you know, one part where we did a speaker dissection, but rather, you know, the whole process after and what we've learned about speakers. And then engaging these students in authentic disciplinary discussions. So having them actually talk to each other and think about, what have I learned throughout this unit? So what we've done so far is really talk about creating that gotta have checklist. And once we have that gotta have checklist, we want them to construct the explanations. And one of the common ways we construct explanations is through the use of CER, or our claim evidence reasoning. Okay, so our claim is our answer to the statement. Our evidence is our data and the details that support our claim. And the reasoning is the how or why the evidence supports the claim. So a lot of times when I had my students produce these CERs, I always told them, your claim and your evidence, you're kind of just regurgitating. You're not explaining to me the science yet. It's that reasoning that is that most important part that ties all of that science together. And once my students understood that, they really focused on that reasoning to show their learning and understanding. Because the claim and evidence was easy for them. They felt great. They're like, I've got this. And then they get to the reasoning, they're like, I don't know what to put. Like, well, what science explains that? What science have you learned that helps you explain that? And that was always like a big hurdle for me to get better CERs and to help like scaffold that for my students. So here is a template for creating scientific argumentation. So on this last slide, we've looked at modeling, we've talked about explanation. So now we're going to look at a little bit of argumentation with those explanations. So this template divides it into that claim, evidence, reasoning, and it has some sentence frames for students. Then it allows them to get comments from peers for improving their work. So giving that peer feedback is an essential part of SEP7, that critiquing component, allowing students to look at each other's explanation and really think about, are they answering the question? Is this evidence relevant to their answer, to that claim? And are they making the correct inferences? Are they understanding, the science behind it? Then allowing students to come back and revise their claim. So we're going to watch a short video of a phenomenon and then show you an example of a CER with feedback and a revised claim, evidence, reasoning. So for those of you that may not know, this is the Tinker Cart video. So for anyone that hasn't seen it, very short video so we can see the phenomenon.
760. Gewonnen hat Herr Dr.
So just a fun video, but that was the video that was used for this group of students, to create their CER. And I believe this is in the participant deck. So you can kind of zoom in a little bit better. But you have the claim, evidence, reasoning, and really looking at how did the questions that were asked in this peer feedback help improve that CER. And again, it's a tool that could be used. This could be just feedback from teacher before going into that final CER if you wanted to do it peer. Super powerful. But sometimes we want to be the ones, right? We're like, wait, we need to make sure. Or maybe you just give feedback on the reasoning, have students give the claim evidence feedback, and things like that. But you can see how this template is used and can be used for that scientific argument. All right. So just like with every other practice, we have a wonderful AST tool that can help guide you in planning for this. So as you're going through each step, really what you're thinking about is what questions am I going to ask students when we get to this point in the lesson. So what you need to listen for, it's usually good to start here. The steps are here, but if you can see, will students be able to verbally describe parts of the explanation but not represent the drawing? What questions could you ask to help guide them to being able to represent it in a drawing? So what does that look like? What are you envisioning? Things like that. And then after you teach it, what did you actually say to the students? Where did you change your questions? Where were you able to stay on par with your questions and things like that? So again, a planning tool. So as we come to the end of our time and the end of our series, right? This is the last practice in our series for ambitious science teaching. We want to give you guys some time to kind of reflect. So we have these two questions for you. And I think we can still, maybe we'll just share out, give you guys 2 minutes to kind of read the questions. Which practice has inspired you the most to change your approach to science instruction? They're listed there. And then how do you plan to carry and apply this learning of the ASTPs into next school year, the end of this school year and next school year? So I'll give you guys a couple minute to think about it, and then we'll take some time to share out. The first question, which practice, and I guess the why of why that practice influenced you. Please feel free to unmute or put in the chat.
I'm really interested, like working on this session, not because it's the one that I remember, but in high school, like really we're struggling, same thing, like to connect like students' reasoning. And just what you said, I mean, claim and evidence is there, and with our English class, they're doing the same. So it's like, you know, let's get together and put all these things together. How could we, like, you know, work together as a whole school? Like you have the same thing. So like I will be starting my new set of students on Monday. So I'm just like, while you're talking right now, it's just like my mind is blowing really on how to like really try to practice this with this last group of students I have. And I really like the tool of the claim evidence reasoning that you give, like the last template. And it's my first time to see such, like I always just use the CER basic template. So I'm just hoping to use it this quarter. We have Q4.
Please let us know how that goes. Always let us know. We're always interested and love to hear. But thank you for sharing. I appreciate that. Anyone else?
Well, for me, you know, I mean, number one to me, as in sort of practices, planning for engagement with big science ideas. I mean, you got the big idea, but then it's, to me, it has to be broken down into the anchoring question or the anchoring event, or the phenomenons or the sub-phenomenons, and tackle each little subunit that I'm teaching. Like on the balloon one, going up, to me, you gotta have something there about density. I guess buoyant force, all right, but to me, you have to have something about density, but all that stuff would have to go into, anyway, you got the big science ideas. I need to break it down in more methodical, 1, 2, 3, and each little event that I have, how do I plan to carry out this idea? What to have a little anchoring event, time permitting, and as many as I can, and then bring it back. But after this meeting, I'm going to ask a couple of people, what is the anchoring question on some lunar eclipse and also the phases of the moon? I mean, I just went through that, but well, I will ask that at the very end, as in what your suggestions or your examples of a phenomenon to explain solar eclipse. I can explain whatever, but what would be your phenomenon, or would be the anchoring event would be the solar one, but the phenomenon, and then how to teach the phases. What would be the big question before I teach myself? What would be the big question before I teach or the big phenomenon before I go with the solar phases or the eclipses, or also you got to teach the revolution of the earth and all that. Anyway, that's kind of, I gotta get more methodical, more organized, and hit every single lesson with a main idea, phenomenon, and that way maybe they will get more science, or then I could really then gear my questions or my final exams or exams, whatever, that they get it. Okay.
Yeah, and I think that's a huge one, right? Planning for these ideas and then realizing like, okay, this is a big idea. How do I break it down for students to really understand the things that I want them to understand? So thank you for sharing, Ruben. I think we have a little bit of time for one more, if anyone wants to share. No? Okay.
Ruben, in the chat, I placed a link to the Open Science unit on Earth and space.
Yeah, I'm reading it, and it says, how are we connected to the pattern we see in the sky and space? So that would be the overlying anchoring question to the unit.
Yes.
And then my sub categories would be maybe, what causes the eclipses, or there is an eclipse, that's the phenomenon. Let's explain why it happens. Or there are phases of the moon. Let's go, explain it. But then we come back and then we answer this anchoring question, I guess. I don't think that's a phenomenon, or is it that's just a question.
Craig, this is a new program, openscience.org, or it's just an site that we can use as a resource, or there are lessons already created there, or what is that?
Yes, Open Science. Open Science is an open source science unit. They have open source science units. They've completed all of the lessons and units for middle school. So you can go to that link and check them out. And Ruben, the event for this one, click in and read through the unit summary, and it talks about the anchoring event for this unit. You could check that out.
I'm bookmarking this page right here.
Yeah.
Yeah, see, I just need to know kind of how is it organized from a big question, and then breaks down into phenomenons, and give me some examples. And once I get enough examples, I will use them, modify them, or and take it from there. I'm not here to reinvent the wheel at all.
Yeah, exactly. This is a great place to look so that you don't have to reinvent the wheel. They start with a big science idea. They start with an anchoring event. They have the anchoring question, and they break it down into all of the supporting lessons.
Okay.
Thank you.
You're welcome. So thank you.
Yeah.
Kirsty, were you going to go ahead, Kirsty?
Thank you everyone for being here. I put the sign out and the evaluation link in the chat. Please, please, please do both. We do look at the feedback and appreciate the feedback. And we're all here to support as best we can, and can try and point you in the directions that we know and understand. And if not, we can always explore together. I think that's a fun part of this job that I like, is that I may not know everything, but I have fun exploring things with everyone. So thank you. And once you guys have completed those, feel free to sign off. If you have any additional questions, you can stay on as well, and we can talk through those and see what we can come up with.
Thank you, too, Paul.
Yeah,
Thank you, everyone. Good to see you.
yeah, thank you. Bye.
Craig, I have a quick question.
Yes.